Hey YouTube, and welcome back to Tech Talks. Today we're going to be taking what we already know about Big O Time Complexities and seeing how we can use that knowledge to improve the runtime of our algorithms. Now, last week I released a video that talks about what Big O notation is and went through some of the most common algorithm runtimes. I also spoke about how you can identify these common runtimes in your code, which is super useful for software engineering interviews. So if you didn't get a chance to watch that video, I highly suggest that you go back and watch it before continuing with this one. I'll drop a link to that video down in the description below. But if you've already watched it, you're all set. If you're new to this channel, welcome. If you want to hear about various computer science and software engineering topics, from programming tutorials to deeper topics like continuous integration, continuous delivery techniques, to even more advanced topics like architectural design and much more, please hit that subscribe button and click the bell icon to be notified about when I upload new videos. Now, let's take a look at how we can write better code with algorithm runtime analysis. Let's dive right into a common whiteboard coding interview style question called TwoSum. In fact, the TwoSum Coding Question is the first one that most people solve when practicing coding questions for software engineering interviews, as it's one of the very first that you'll encounter on coding preparation websites such as LeetCode. The question goes as follows. Given an array of integers and an integer target, return the indices of two numbers such that they add up to the target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So the first thing we can do is think about some input and output examples. For instance, if we have an array of integers 11, 2, 7, and 15, and a target of 9, we want to return an array with the indices of two numbers that add up to 9. In this case, it would be index 1 and index 2. Another example would be if we're given an array of integers 2, 4, and 3, and a target of 6, we should return an array containing index 0 and index 1. You get the picture. So you might have already been thinking about how we can solve this with code. The first thing that usually comes to mind is a for loop that is nested inside another for loop. The outer loop iterates through the array, and the inner loop iterates through the remaining integers and compares them to the number tracked by the outer loop. If they add up, we know that these are the indices that we want to return. Let's step through one of our example datasets and see how this algorithm computes the answer. Given an array of integers 11, 2, 7, and 15 and a target of 9, the code will start by taking the integer 11 and comparing it to 2. We can see that this doesn't add up to 9, so then we compare 11 to 7. As this also doesn't add up to 9, we compare 11 to 15. Since this doesn't add up to 9 and we are at the end of the array, we break out of the inner loop and start the comparison again, using 2 and 7. Since these both add up to 9, we know that we have found our indices, and we return them in an array. But let's start to think about the runtime complexity of this algorithm and imagine the worst case scenario. What if we're given the numbers with 2 and 7 in the final indices of the array? In that case, we would have to loop through the whole array 6 times. That's not very much for our simple example dataset, but what if we were dealing with millions of integers in the input array and we encountered the worst case scenario? We would have to loop through the array millions of times. Of course, we know from the previous video that this algorithm's runtime is described as big O of n squared, which isn't very performant. So what can we do to improve the runtime of our algorithm? Well, what if there was a way that we could compute our answer by only visiting each integer once? That would get us to a much better runtime of big O of n, also known as linear. We can achieve this runtime by using a data structure known as a hash map. A hash map is a data structure that stores items in key value pairs, and you can access them by an index of another type, for example, an integer object. So in our case, we can use this hash map to store the integer at I, and then as we continue to iterate through the array, we can check the current integer against all the previous integers in the hash map to see if any of them can be added to the current integer to equal the target number. As you can tell, this is a much faster runtime, and in fact it is the optimal solution for the TwoSum question. Let's look at how this implementation of our algorithm computes the answer in our example dataset. set. We start by comparing 11 to all of the keys stored in the hash map, which right now is empty. We see that there is nothing in the map that can be used with 11 to equal 9, so we store 11 as the key and I, which is currently 0, as the value. Then we move on to 2. We check the hash map again to see if there's anything that can be used with 2 to sum up to 9, and find that 11 plus 2 does not equal 9, so we store 2 and the current index, which is 1. Next, we are at 7. So once again, we look at the hash map and check to see if anything in there can be added to 7 to equal our target of 9. Well, 11 can't be used, however we can use 2 with 7 to equal 9. Now all we need to do is return the value of the index of 2 along with the current index at I. As you might have already noticed, we only visited 3 elements in the array and we didn't even loop through the whole array once. And of course this is a much faster runtime than the brute force solution. As a final explanation of the runtimes on this problem, let's take a look at a unit test that measures the time taken to run through the same dataset for both implementations, and then we'll look at the average amount of time that it takes. For simplicity, we'll run through each implementation 3 times and then just take the average time for each. As you can see from the console output, the brute force solution, or Big O of n squared solution, took an average of 55 milliseconds to complete, and the optimal solution only took an average of 3 milliseconds. So now you know how to use Big O notation and algorithm runtime analysis to improve your code quality, but I want to hear from you. Is there anything that you'd like clarification on, or perhaps there's a different topic you want me to dive into? Let me know in a comment down below. If you want to learn more about Big O notation and algorithm runtime analysis, check out the featured video on the left, or if you want to learn about something completely different, check out the video on the right. Thanks for watching. Don't forget to like this video and hit that subscribe button, and I will see you next time on Tech Talks.